Okay, so yesterday I ended up with the cartoon sort of discussion of effective field theory. Okay, and basic idea is that quantum field theory emerges from the known at some ultraviolet scale lambda, and it emerges endowed with basically all the interactions you can think of. And now these interactions can be classified into three classes, depending on the dimensionality of the coupling. Couplings of positive dimension here, zero dimension, and negative dimension. Okay, and then by simple dimensional analysis, computing observables at any energy E below this fundamental microscopic scale, lower energies, then you can assess the contribution of each of these couplings as a function of energy in the following way. Okay, in particular, the couplings that are associated with positive dimension are those associated with operator of dimension less than 4, have an effect that grows with energy. An example, the typical example is mass. Okay, mass is a coupling of dimension energy square, and it's not very important that high energy much bigger than the mass. When particles all behave like photons, they are moving at the speed of light. But as the energy gets smaller, then you realize that the particle has a mass. If you want, just make it as simple as that. And then there are couplings of negative dimension. Okay, those are the vast majority, and they are associated with operator of higher and higher dimension. Okay, they are the infinite tower of these operators, and these couplings, their effect decreases with energy, and it decreases with the power of energy. So you can imagine you go down by a factor of 10 over 100 in energy, and you get immediately effects, suppressions that are 1,000, millionth, billionth, and so on and so forth. So they become very quickly invisible. And then there are couplings that are resilient, okay, that have zero dimension, and so they are roughly equal important or unimportant at all scales. Their effect is. You discover that for these couplings, the behavior is logarithmic, okay? And of course, if you really extrapolate this behavior over very, very exponentially wide ranges of scales, you can have a sizable effect. That's the well-known renormalization group evolution of couplings, okay? So that's the situation. One thing that should be said is that theories like the ones we're mostly familiar with, theories that are weakly coupled, that are basically free theory perturbed by weak perturbations, the dimensionality of all these couplings is integer, okay? It's integer because derivatives have dimension 1 and the fields have dimension 1, or in fact, if they are fermions, have dimension 3/2. And putting together this integer of integer dimensionality together with Lorentz invariance, you will only have integer dimension couplings, okay? But there's a specific property of weakly coupled theories, and I will comment on this in a moment, okay? So this is where we were yesterday, and what I would like now to do, just taking this attempt at writing, okay, is to broaden slightly this perspective, okay, and including also the case, at least formally, of theories that are not really weakly coupled, okay? And let me argue in the following way. Okay, now I have to change. I'll move to this one here. So let me give you the basic picture I just gave. Okay, so this is energy, and there is some scale lambda where we start. Okay, this is the UV. This is the known, okay? We don't know what there is here. We haven't done measurements. The only thing we know is that below this scale, there is some effective field theory, which in the simple case of this toy scalar theory, but of course we can think of more general cases, there is a kinetic term, and then there's the mass term. We can even consider cubic coupling, quartic coupling. Okay, well, plus or minus. Don't pay much attention to the signs here, right? 5 to the 4th. And then in these dots, I put everything, even higher dimension operators, which also involve more derivative, more fields. Okay, and just compatible with what I said before, the relevance of these effects with energy, this goes like m squared over e squared. This goes like G3 over E. This goes roughly like G4. This goes rightly like G5 times E, G6 E squared, and more powers, okay? More and more powers of energy. So you have the situation that as soon as you start looking at energies below lambda, all these terms here, the operators of dimension higher than 4, their effect quickly go down with energy. On the other hand, the effects of operators of dimension strictly less than 4 grow with energy. And of course, if I were to take, if m were of order lambda, there would be nothing to discuss, right? I mean, there's no regime where we can use this theory. So we're interested in a situation that for some reason that we will later investigate, this m happens to be very, very, very small, okay? So the effect of the mass when you start, this is just, at this stage, it's an hypothesis, it's a working hypothesis, and then we will later debate it, okay? But we start with this very small mass, and then its effect will grow, okay, as we go down in energy. Similarly for the cubic coupling, okay? Well, here as well, if we take this cubic coupling of order lambda, immediately this coupling becomes strong. As soon as we go below lambda, if G3, which is dimension 1, is of order lambda, then you go 100 times below lambda, its effects are huge. In fact, so huge that even the vacuum is unstable because it's a cubic interaction. So in some way, structurally, this coupling has to be small. In fact, it turns out that this coupling, I can refine the statement, okay? But G3 cannot be much bigger than M. So these guys here grow, okay? They grow, and they grow until at some scale, let's say this is our UV, and this is IR, okay? Essentially, we can view quantum field theory as a trip from the journey from the UV to the IR, okay? It's like the guy that goes far away, and then in the example of the multiple, we go from the UV, from close to far away. And here, the IR is the scale where these couplings that were small perturbation to start with, they become important. So what is the IR scale is simply characterized by M, is simply of order M or G3, okay? In fact, controlled by the G3 could even be 0, right? If you have a theory where you have a symmetry phi goes to -5, you don't have G3. So what matters is M, certainly, and possibly also G3. That means that in the middle at energies that are much smaller than lambda, than our ultraviolet microphysics scale, and much bigger than, say, M, physics is well described by just the terms of dimension 4, the terms whose coupling has no dimension. Okay? All the other effects, either because they're dimension larger than 4 and they went down to 0, okay, or because they're not yet large, these are the mass effects, are negligible in this intermediate range. So in the intermediate range, you have just essentially this. Now, there's one important, so this is essential. What I've been using here is not very much, okay? I've been using dimensional analysis. I've been using the fact that I want to use quantum field theory, okay? and that quantum field theory arises from some scale lambda. Okay, some scale lambda, there's this field that may be composite from new dynamics at scale lambda. So for instance, our template for this is given by QCD, which I will mention in a moment, where lambda is the QCD scale, and below the QCD scale, the field here is the pions. Okay, so that's an example. And so in this intermediate range, the physics is dominated by the purely dimension 4 Lagrangian. So what is peculiar with this Lagrangian? What is peculiar is that, first thing, what is peculiar about this Lagrangian is that it is approximately scale invariant. Okay, it's approximately invariant under the symmetry phi goes to lambda phi lambda x. You can check that this is a symmetry, okay, that the action is invariant under this transformation, okay. And this is simply, given any configuration, you're simply, there's a certain field configuration, you simply rescale coordinate and rescale fields in such a way that the action is invariant. So particularly if you have a solution, okay, of the equations of motion, just working classically of this Lagrangian, you do a transformation like this, you get another solution. So this is a symmetry. And if you want, now this symmetry is not exact because first of all, there are the small perturbations, and also quantum mechanically, actually, the effects of G4 are not scale invariant because of renormalization effects, okay? There are logarithmic scale dependence when you go beyond 3 level, okay? But if the theory is weakly coupled, this, which may or may not be, but if it is weakly coupled, and this is just an empirical fact that we keep finding weakly coupled theories, of course, sometimes they are not, but they are just a fact of life, weakly coupled theories. Weakly coupled theories, in the case of weak coupling, the breakdown of scale of dilatation symmetry that arises at the loop level is small, okay? It's of the order of the loop expansion parameter. So what we have here, we have a scenario where there are two, it's like you're on a highway, there are two tool booths, okay? One is the IR and the other is the UV. And here you pay the toll. Here you have couplings that depend very fast on scales, okay? These couplings are depend very, when you go to energy of order M, these couplings are both important, large, and they depend, their effect changes quickly. Dynamics is different. Similarly, when you get at the very high end, at the other tool booth, there you pay the other toll, the couplings of dimension higher than 4 are important, and they have a strong energy dependence. In the middle, you just cruise. In the middle, okay, you are on the highway, and you have essentially a scale invariant Lagrangian. Scale invariant Lagrangian means that you're doing,
your audio is a little bit cut, so maybe it's better if you switch off your video for a better connection, maybe.
I see.
Yeah, sometimes you are, we don't hear you for like a second or so. And
oh, that's weird. So was it the case yesterday as well, Riccardo?
No, yesterday was a little better. So
I wonder whether there is somebody.
Your video gets stuck sometimes, and you
okay, take away the video.
Yeah.
I'm not sure it is the video, but I'll try.
Yeah, we can try. Yeah.
It's a pity because, yeah, okay, it's okay. Not. Yeah, I cannot gesticulate.
That's right.
Okay. That's terrible.
Unless
okay.
you have a way to improve your connection. Maybe, I don't know if you are in the same place or.
Look, I don't know what to say. I don't know what to say. Sometimes. Let me check if my wife is doing. Give me 1 second, okay? I'm the only user. My son even finished his exam, so there's no. Okay, look, let's go on this way. So there is this approximate scale invariance. So in a sense, what you have is between these two scales, you have a theory where things change little when you change your energy. Okay, you have what the most boring situation for experimentalists, the one that we call the desert. You improve you change your energy, you increase the energy, and the only thing you see is a slight change in the effective value of the quartic coupling, but that's it. Of course, if you were to increase the energy and you start seeing these other ones, then bingo. But otherwise, you just are stuck in what we call the desert, okay? And that's just, the desert is, from the point of structural point of view, it's a theory that is approximately scale invariant. This is the first thing I want to say, and I will mention this more in a moment. This will come back again in a moment. The other thing I want to say is that now, the fact that the infrared scale is determined by a mass or by a cubic, which is to say couplings of strict dimension less than 4, it's a peculiarity of scalar field theory. In other cases, in fact, perhaps other interesting cases, it can even be where these couplings are absent because of structural reasons like gauge invariance. Then it can be the logarithmic evolution of the quartic coupling itself, or of the dimensionless coupling themselves, to determine the occurrence of the new scale, of the IR scale. That's precisely what happens in QCD. Okay, in QCD, the situation that you have in QCD is this. Okay, in the, let's say that you emerge at you emerge at the scale lambda, which is MW, okay, the W scale. Okay, the theory that emerges there, let's consider a simplified 3-flavor QCD where you have only up, down, and strange. Let's forget for a moment strange and charm. Let's say that they are heavy. This is just to exemplify the idea. So, and the masses of these light quarks, up, down, and strange, are so small that they don't play a real role here. So they just being very sloppy with coefficients, minus d nu, g nu, plus I, g mu, g nu. I should put the coupling. I, g strong, g nu, squared, plus there is the quark fields, q, iq, gamma mu, d mu, minus I, g strong, g mu, q, plus higher dimensional operators, okay? So what you have here, you have a situation where you don't have any interactions of dimension less than, any truly important operator dimension less than 4, like you had in the scalar. The leading effects are, even in the far IR, are determined by the coupling. This coupling is dimensionless, but it evolves logarithmically, okay? And well, this logarithmic evolution over many decades of length generates a new scale. And this is the QCD scale, which is the scale where the effective coupling, running coupling, the effective running coupling of energy becomes of order 4 pi, okay? This is the scale where this coupling becomes strong, and here you have confinement, you enter a new regime, and the description you had at higher scales in terms of weakly coupled quarks and gluons gives way to another description, which is valid at lower energies, below here, okay? And that description in terms of pions, where the Lagrangian is the pion field. I'm not even indicating the indices, but roughly something like 1 over QCD square. And these pions are Goldstone bosons, and they only have derivative interactions. Okay, so they're like, they're scalars, but they don't have at least a mass in the limit where the quark masses are 0. And so again, what you do here, you move from a UV description. The UV description here is essentially free, where this is the linearized G mu nu, okay? Free G mu nu plus free quark, free massless quarks, plus interactions proportional to GS, okay? Again, in this situation, what you have free field theory, approximately free field theory that is scale invariant, perturbed by a coupling which is dimensionless at the level of naive dimension, but evolves logarithmically when you consider higher order effects. So it's, again, approximately scale invariant. So again, you have a situation where QCD between the W mass and lambda QCD doesn't do very much, okay? It's just, it's always the same. It becomes slowly more strongly coupled, or when you go below, or more weakly coupled when you move up the energy, but essentially it remains the twin theory. So you have an approximate scale invariance. Same thing here, when you go below, okay, but then eventually you will get to the pion mass, which is slightly below, which is determined by the quark masses. But in the between these two scales, again, this theory behaves to a good approximation as a free, the theory of a free scalar, okay, plus this small perturbation, okay, as soon as you are at energies below lambda QCD, this can be the small perturbation. So again, you have an approximately scale invariant theory, as long as you are at energy bigger than the pion mass. So you see, it looks like these theories, we know, they live in stages. They go their structure is truly, it's like when you move on a highway, you go from one tool booth to the next, and there are the tool booths are the points where there are some where there is a change, a rapid scale dependence due to the fact that you are encountering mass thresholds, and in between these thresholds, the theory behaves approximately scale invariant. Okay, just give you an example. Again, even the whole picture of physics, one possible physics beyond the standard model picture is W 10 to the 2 GeV. And here you have the standard model, the weakly coupled standard model in the between, which is approximately scale invariant, right? It's a weakly coupled field theory. In this range of energies, you can neglect the Higgs mass. You only have Yukawa and gauge couplings and Higgs quartic. So these are the only parameters that matter here, plus the kinetic terms. So again, in this we call, if this is the situation, in this desert, you have an approximate scale invariant theory. Very much like in the case that described before, there is lambda QCD. In the between, there is scale invariant, and then there is the pion mass. In fact, there is also the muon. And again, so it's all stages like this. Now, it turns out that this picture of quantum field theory of being simply described by approximately scale invariant stages between thresholds is valid beyond perturbation theory. And we have examples of these in condensed matter systems that we can study both numerically and also in the laboratory, and in specific classes of formal four-dimensional quantum field theory, in particular when theory is endowed with supersymmetry, which can be constructed because of the various constraints allowed the help in addressing dynamics, which is provided by supersymmetry. In other words, there are examples of theories that have precisely this feature of scale invariance, even though they're not weakly coupled. Okay, the example I've spoken so far, they are they are all theories that are to the good approximation free field theories. Okay, free field theory is scale invariant. Okay, free massless field theory. Okay, actually, the notion of scale invariant field theory also features examples at finite coupling, in particular even at strong coupling. Okay, so now it turns out it's a fact that such theories, and it's a fact of life, okay, which is highly debated, is certainly proven in the case of weakly coupled theories, but it's most likely true also for strongly coupled theories. Theories that are endowed with scale invariance, global scale invariance, are also endowed just as a bonus by an additional sort of local scale invariance, where you do dilatations that are different at different points. These are specific classes of transformation called conformal transformations. So quantum field theories that are endowed with scale invariance basically always automatically are endowed with a bigger symmetry, which is called conformal symmetry. So these theories are called conformal field theories. Okay. Strictly speaking, non-trivial conformal field theories in particle physics so far have not been observed, but we know they exist. Okay, we know how to construct them theoretically, and we have examples in condensed matter and statistical mechanics. For instance, the Ising model in 3 dimensions at the fixed points is a non-trivial conformal field theory. So it's an interacting scale invariant theory. Now, why I'm telling you all this? I'm telling you all this because if you want to build, think of ideas beyond the standard model, it's good to have a broader perspective than just the theories you've been encountering so far, particularly weakly coupled theories. Okay, so now, and the reason why I'm bringing this up again, because I'm discussing around this issue of basically what is quantum field theory, right? I'm giving you this picture that quantum field theory emerges from the UV, then it lingers close to a scale invariant dynamics for many decades of energies, and then eventually it reaches another threshold. Now, the examples I gave you before are all weakly coupled theories, but you can think of this as happening also in strongly coupled theories, and the idea is the picture, okay, is that your theory emerges from some UV scale is the action of the scale invariant theory, CFTs, okay, plus small perturbations, okay, very much like we did before. Before, we started with a free field theory, which is scale invariant, plus small couplings. Here we start with the conformal field theory, which shares with free field theory just one property. It's scale invariant, in fact, conformal invariant. But that's it. But it's interacting, so it's very non-trivial, to the point that when it's strongly coupled, it's even difficult to really write down the useful Lagrangian with which you can work. But these objects, we can control them indirectly somehow, okay? And then there are deformations of two types. There are the relevant and the irrelevant. Very much as before. The relevant are let me call them with index alpha, G.
Riccardo, there are two questions actually.
Yeah, please.
One question is
the question is, why are you telling all this crap? Okay.
No, is that you say that almost every time we have scale invariant theory, we have conformal invariance. Are there
we don't have any example at the interacting level in unitary Poincare invariant theories. The only examples we have are non-unitary theories.
Okay, where we have scale invariance but not conformal invariance.
Yes.
Okay.
Unitarity plays a very important role here. At the weakly coupled limit, you can prove that this is not possible.
Okay.
I actually contributed to the proof. It's quite indirect, so it's not something that we can discuss here on the spot, but the weakly coupled case, yes.
Okay,
So
thank you.
all the theories that you can build using weak coupling are also conformally invariant.
Okay, perfect. Thank you.
Catherine?
Yeah, thanks. My question is similar, just a little bit more basic. What is the difference between scale invariance and conformal invariance?
As I said, so scale invariance, as I said, it's this. Okay. Are you with me?
Mm-hmm. Yes. Mm-hmm.
And conformal invariance is a more complicated thing. It's a transformation where you do an inversion, you do a translation, and then you do again an inversion. So let's view it this way. You send x mu into x mu over x squared. You invert it. Then you translate it. And then you invert it again. Now you can compute this, okay, and well, okay. Look, this is some expression. What is important is that these transformations, okay, are transformation where locally, okay, let's say you have locally some space like here. Are you with me?
Yes. Mm-hmm.
And it means that locally, at every point, so if you have lines that are orthogonal, they get mapped into lines that are also orthogonal, like here. Mm-hmm. Okay. However, the space may be curving itself. Okay. So for instance, you can have some pattern like this that maps into something like this. So in particular, you can map lines into circles, okay? And but the transformation is this one here. You can work out this transformation here, okay? And that's what it is. I don't know whether this is very useful at this stage.
No, that helps for sure.
Okay.
So why does scale invariance imply that there will probably be conformal invariance?
The basic story is this, okay? But by the way, can we postpone this to the discussion session? Otherwise, I will never get. This is going to take
yes,
another 10 minutes.
Absolutely, that sounds great. Thank you.
Yeah, sorry. Otherwise, then I will have to rush up. Sorry.
Sure, no worries. Thank you.
I think we can leave this. We can leave this to the. But the idea is basically this. Okay. Translation invariance is telling you that there is a. But by the way, the Noether theorem is predicated on local coordinate transformation. I mean, the space-time symmetry have to do with local coordinate transformations. Okay. So what generates local coordinate transformations? Well, is the energy momentum tensor, is the related current. Now, what is the energy momentum tensor? Energy momentum tensor is the current associated to translations, right? Are you with me? Sorry. Okay, let me put it this way: the energy momentum tensor is the conserved current associated with translations. Now, translation does not imply also Lorentz transformation. If you have Lorentz transformations, well, Lorentz transformations is made of what? Well, it's made of 6 generators. Okay, 6 generators that represent antisymmetric tensors under Lorentz. Well, the constraints imposed by Lorentz transformation, the antisymmetric on the energy momentum tensor, simply amount to having the antisymmetric part of the energy momentum tensor equal to 0. Now, what does dilation do on the energy momentum tensor? Well, it sets its trace to 0. Now you can prove in a very simple way, it's a one line almost, I can do it later on in the discussion session, that if the energy momentum tensor is traceless, then you also have another conserved current, which is associated with conformal transformations. I will discuss that. I will prepare a discussion for the discussion session. Okay, let me recover where I was. Okay, now I have to catch up where I was. Okay. So again, so you have this two broad classes of effects. Let me indicate this with A. The irrelevant, I indicate them with index A, and the operator is I irrelevant A. Okay, and each of these operators will have some dimensionality. Okay, let me call the dimensionality. Let me indicate it this way with a bracket around the operator. But let me call it easier like this, delta. This is the dimension of the operator, okay? Which just tells you how the operator scales under dilatations, okay? And then the effects of the physical effects of these couplings is what? Is G R alpha E to the 4 minus delta R alpha, and the same thing for the others, right? So the relevant operator are those operators have dimension less than 4, and you see that their effect grows with when you decrease the energy. And here you have the other way around. Here the dimension is less than 4, and here is bigger than 4. And of course, if the operator has dimension exactly equal to 4, then there's no energy dependence, at least at the lowest order. But let's stick to these two cases, dimension relevant and irrelevant. Okay, so you have these ones here. So the effect of these operators here will decrease with energy. So then what happens? So the picture is that you emerge from the ultraviolet with this quantum field theory, which can be written as a maybe strongly interacting conformal field theory, perturbed by some relevant and irrelevant interaction. The irrelevant interaction, if you're allowed to go to lower energy, they become quickly small perturbations because their effect decreases with energy. It goes like a power of energy when the energy decreases, it goes like a positive power of energy. When the energy decreases, the dimension here, oh, damn it, I'm doing the other way around, delta. A minus 4 again. See, if the dimension is bigger than 4, this goes to 0 when the energy goes to 0. So what do you say? It emerges, and then these effects quickly go away when you go towards low energy. So they decrease, and while these ones increase. Okay, until you reach a scale, which is a scale where some effective relevant coupling becomes of order 1, very much like the QCD coupling. And here, when this happens, it means that you are order 1 away from a scale invariant theory. And this is, interpretation is precisely suggested by what happens in QCD. The quantum field theory here will run into a new regime. Possibly your degrees of freedom will rearrange, they form bound states, and the theory will emerge below the scale, either with no light degrees of freedom, perhaps everything gets a mass and you have a gap, or only a few light degrees of freedom will emerge with other interaction and you go to the next stage. But in the between, you have precisely the situation. The theory is just like a scale invariant theory described by a fixed point of the renormalization group and the form by these couplings that evolve. And the dependence on decoupling of energy is nothing but the renormalization group, okay? The renormalization group evolution. So you can view, let me just present it here. the evolution. In fact, you can view this on this plane. I draw your couplings. Okay, on this line, I put the relevant ones. I just reduced this infinite. I forgot to say the set of relevant couplings. It's a fact that even in this strongly interacting theory, the number of relevant couplings is always finite. Okay, and there is again perhaps a deep understanding of that one could give, but that's always the fact, and that's precisely like in the weakly coupled theory we studied before. So you only have a handful of them, while here you have an infinity. Okay, but still, let me draw on this plane two broadly the relevant and the irrelevant couplings here. Okay, and this arrow indicate the RG flow, and this point corresponds to the exact CFT. In other words, to the point where you have no perturbation. Okay, and of course, if you're exactly here, you're not evolving. That's a fixed point. And now, what is the picture that I just drew before? Okay, what is the picture? Let me perhaps make it smaller. Can I make it smaller now? Okay, go to hell. So the idea is the following: you start in the ultraviolet here. What point is this? This is a point where this is the typical UV point. What is it? It's a point where the irrelevant coupling is large and the relevant coupling is small. You're here, okay? So you're precisely at the point where the irrelevant coupling haven't yet been reduced and the relevant one haven't yet gotten bigger. And then when you decrease the energy, you move along this trajectory. The irrelevant coupling becomes smaller and the relevant coupling grow. Okay, and in the middle, it doesn't look like, but most of the RG time for the vast majority of energies, you are near here, which is to say that you're near to the fixed point. Okay, so basically you go quickly here, you go down quickly here, you linger around here, and then little you move, and then quickly you go to the relevant point. Okay, and here when the relevant coupling become large, you exit again the fixed point because you're far away from the fixed point. You go, so in other words, you start that you're not really still away close to the fixed point. The relevant coupling becomes small, and then do that. Okay, but you see, in order to be able in order for this scale separation to be large, you have through your RG evolution to get very close to this point here. Okay, which means that you have to start peculiarly, because if you start here, you go very quickly, okay? Which corresponds to the fact that you start with relevant couplings that are already large. Okay? In other words, the crucial thing to have a separation of scales is to start you're close on this line, okay? You're like here, and then you move away, okay? And in a sense, the presence of this other higher scale is simply signaled by the fact that you are eventually driven again away from the fixed point. So in other words, again, the picture is usually this: you approach a fixed point, you linger close to it, and then you run away. Okay. And while you linger here, all the irrelevant coupling becomes smaller and smaller, and the structure of the theory simplifies. Okay, I'm saying this because we ought to think in a more general way about how to get separation of scales, and this will come back later again when we discuss the hierarchy problem. So now let me get back. Or maybe I have time for a few questions, and I want to get back to where I was.
There is one comment in the chat. I mean, one question in the chat, but
yeah, sorry, I had to rush this. Yes, is there an intuitive reason to why the relevant coupling should be finite? Yes, one interesting property of this class of theories, conformal field theories, is that you can deduce the same dynamics on any space that is related to the space we are studying by a simple rescaling, local rescaling of the metric. And using this remark, you can study quantum field theory not on the plane, but on the cylinder, okay? Because the metric of the cylinder plane are precisely related by this local rescaling of the metric. And once you are on the cylinder, you discover that each of these operator is associated to a state in the Hilbert space. And on this description on the cylinder, the dimension of the operator is the energy of the state. So in this description, the statement that there are only finitely many operators of dimension less than 4 is the statement that there are only finitely many states of energy less than something in a compact space. In other words, it is just, so the space on the cylinder is just a finite volume, and the Hamiltonian as a discrete spectrum. So below any energy levels, there's only finite number of levels. It's as true as that. Is this clear? So it's the same as the statement that a Hamiltonian with discrete energy levels has only, and stable, in other words, that the Hamiltonian is bounded below, has only finitely many energy levels below a certain fixed energy.
Yeah, it's clear. Thank you. Thank you.
Is this clear? No.
Yeah, I think he said yes.
Okay. Very good.
Then there is another question.
Okay.
Oh, I'm sorry. I accidentally pressed it. I don't have a question. I'm sorry.
Oh, okay.
Okay. Now I want to get to another aspect which is crucial in the whole discussion about BSM and how we should think of the standard model structurally, and this concerns symmetries. Okay, so we'll mostly be concerned with. Can I get back to the picture and maybe if my voice goes away again, Stefania, please tell me that I will take the picture away.
Sounds
Not
good.
being able to move my hands makes me very, very nervous and doesn't work too well. Can you hear me?
Yeah, we can hear you.
Okay.
Yeah.
So I will mostly be concerned with global symmetries, possibly approximate. The gauge symmetries are another story. Okay, well, gauge symmetries, in a sense, what we used to say that are not really symmetries. They're should more be viewed as redundancy in the parameterizations that are needed to pin down the truly physical degrees of freedom. Okay, in other words, they're for the photon. Okay, you have 4 fields apparently. Mu is a vector, but you know from the representation of the Poincare group that the massless vector only has 2 polarizations, 2 states, and it's precisely to match because they are truly structural, but they're less important for what I'm about to say. So let me just get to that. Okay. Now, what is the very important part? So what is, there's something very important in what I've been telling you so far about effective descriptions of nature in general, starting with the multiple expansion. I just said that when you go to long distances or low energy, the set of parameters that matter is reduced because the vast majority of multiples or the vast majority of operators will have effects that are suppressed when the energy goes to 0. So this reduction in the number of parameters that matter is clearly a great simplification. You have fewer parameters, so the dynamics is simpler. Yeah, that's right. You have less freedom in what can happen. You have few parameters. In fact, this simplicity is simply related to a small number of parameters, is often associated to a further phenomenon, which is the occurrence of accidental symmetries. Okay, So symmetries just occur because of this simplification. And in order to exemplify this visually, I usually make this spherical cow example. So consider a cow, okay? See the cow here. If you take the cow and if you rotate it, okay, or if you rotate with respect to the cow, you see that the cow changes, okay, because the cow has horns and tails, and if you rotate it 180 degrees, the tail ends up where the head was. So we make this, the fact that we see a difference when we make a rotation is associated with the fact that the cow is not invariant under rotations, okay. On the other hand, if instead of rotating it, we start stepping back and we go further and further away from the cow, or we send the cow away, the cow becomes a point, okay? And from our perspective far away, a point is the same no matter in which direction we look at, okay? It's SO3 invariant, okay? So that's an example. That's the simplest example you can think of an accidental symmetry. And in fact, this example is very much related to the first example I started with yesterday, the electrostatic potential, okay? Again, you take your electrostatic potential, okay? And so there's a local distribution of charge, and then you expand it at large distances, and you have the dipole, you have the monopole, you have the dipole, you have the quadrupole, and so on and so forth. And now, when you are very, very far away, you can neglect everything apart from the monopole. And the monopole, as you know very well, is the same, is 1 over r potential, is the same in all directions. So it's SO3 invariant, precisely like our spherical cow. Now, if you get a bit closer or you become more precise, you may also be able to see the dipole. Okay, it's like saying in the cow, you know where the head and the tail is, just not more than that. Okay, you know the directionality. This, of course, breaks SO3 because the dipole points in one specific direction, but doesn't break it completely because rotations around the direction of the dipole are still a symmetry. I mean, if you have a dipole, you look at it around it this way, it will look always the same. So you have an SO2. So you don't have the full symmetry, but you have a little bit. Once you go to the next level, you have a quadrupole. Generically, you don't have any symmetry left. Okay, so then you really see these stages of if you want, you first start with a point. Oh no, you start with a point, then you get this, and then you get this. Okay, and that's it. Okay. Maybe you have it in a different plane, and then you have all your so this is the prototypical example of accidental symmetries. Moving away from the cow, so it says that my internet connection is unstable. Do you hear me well or not?
Yeah, we had 1 second that we lost you.
Okay.
Try switching off your camera anyway. It was maybe a little better before.
Okay. I must admit that teaching this way, I hate it. Not being seen, but that's okay. So, go to hell here. Okay. So the cow and the electrostatic potential are very basic examples, but the same phenomenon you can think of in particle physics. For instance, parity. Parity has been a sacred symmetry for ages. Okay, oh, parity, parity D, parity here, parity there. What is parity? Well, parity is just an accidental symmetry. And you can see that just by looking at QED. Okay, QED is the ultimate effective Lagrangian. okay? It's the effective Lagrangian describing the lightest important degrees of freedom in physics, the photon and the electron. Of course, there are the neutrinos, there is the graviton, but they're very weakly coupled, okay? So as far as we are concerned in a laboratory, the lightest guys are the photon and the electron. Okay? They're also relevant for atomic physics. And now we can precisely apply our effective field theory ideology or perspective to QED. And again, we start writing our Lagrangian. We write, damn it, no. We write all the terms of dimension 4. We can write mass terms. We can write terms like this. Okay, we can write a mass term with a gamma 5, which looks like it's parity breaking. We can write an FF dual term, which is also parity breaking, which involves the epsilon mu rho sigma tensor, the Levi-Civita tensor. And this is all we can write at the level of dimension 4 or less. Then, of course, we can write an infinite tower of higher dimension operators. But at the lowest order, which is the analog of the lowest dimension operators, which is the analog of the monopole, okay, the leading interaction that you have when you go at sufficiently low energy, well, then you realize that you like it or not, you want it or you don't want it, this Lagrangian is parity invariant. Okay, this Lagrangian is parity invariant, unavoidably. In fact, it doesn't look parity invariant, but you can always redefine your variables by chiral rotation to make it manifestly parity. Or if you want, you can define, there's a certain definition of parity under which this is invariant. As concerns this other term here is a total derivative. Now, then you go to the next order where nature has a chance of breaking parity. Do you think nature gives a damn about parity? Do you think nature doesn't take this chance? It does, okay? As soon as you go to the next order, you have dimension 6 operators, and now we even know what the origin of this operator is. It's from the exchange of the Z boson, okay? We go to these dimension 6 operators and they violate parity. So parity is just a low energy accident in this perspective, okay? And it's as the parity in QED is like the sphericity of the cow that you watch from a faraway mountain, nothing else. Oh, this with a good, of course, there have been people who have been writing papers that had thousands and thousands of citations trying to make parity a fundamental symmetry in the standard model. Maybe yes in the end, but actually it doesn't smell. It's not needed, okay? It's accidental. And there are more examples of accidental symmetry we will discuss later on. Now, so as I said, towards the IR comes often with the occurrence of accidental symmetries. In fact, we can think of symmetries in general in this way, okay? Now, there's another aspect of symmetry which is very, very important, okay? And it's their relations with selection rules, okay? In particular, this is important. It's particularly important when symmetries are not and the presence of symmetry is still important because it gives you important structural relations between observables, okay? And so this goes normally under the name of selection rules, but actually dimensional analysis you're very familiar with is also a selection rule. Dimensional analysis is nothing but the selection rules of dilatations. And I will show you in a moment, okay? So what are these selection rules, okay? It works in the following way, and I will exemplify in a moment, okay? The point is that it's always possible to imagine symmetry transformation under which also the parameters transform. Okay? You can think of the parameters in your Lagrangian themselves as fields or as dynamical variables, and you allow them formally to transform, okay? And by allowing them to transform properly, your Lagrangian will be formally invariant, okay? Now, once you determine these, if you want, fake symmetries, the dependence of physical observable on such parameters will have to respect the symmetry. Okay, we'll have to respect the covariance under the symmetry. Okay? And therefore, the symmetries will give you a very sharp insight on what to expect when analyzing a system or doing a computation. Let me give you an example. Okay, take the simplest thing we can think of. Okay, the classical pendulum. Okay, in fact, I don't know whether it is true or not. I should check. And turns out it's Galileo who started doing these things. And given that we are doing GGI lectures, I certainly have to show you a picture of Galileo here. Now, take the pendulum, okay? Okay, there are three parameters that define the pendulum: the mass, the length, and G, the gravitational acceleration. Now, in this system, you can think of two symmetries, okay? One symmetry is spatial dilatations, okay, under which you dilate coordinates, and time dilatation, under which you dilate time. If you want, I can show you later in detail at the level of the Lagrangian if you were confused what this means, okay? Now, these are not symmetries of the pendulum. They're not symmetry because the pendulum is endowed with parameters, which is its own rigid length, which is not dynamical, and the acceleration of gravity, which is an external parameter, that have dimensionality under the dimension of space, and space divided by time squared. Okay, so they have dimensions, and therefore they would transform. But now, if you consider this L and G as some dynamical parameter, you can assign them transformation. In fact, G is a dynamical parameter. It's coming from the metric. But if you consider them as dynamical parameter, you can rescale them in the proper way and make the action invariant. And the rescaling is what you would expect, right? You rescale the length of the pendulum precisely, you rescale coordinates, and you rescale the acceleration very much like the acceleration is length over time squared. You rescale it this way. If you do this transformation, and you don't rescale the mass, okay? If you do this transformation, the Lagrangian of the pendulum, including, I mean, the action of the pendulum, okay, is invariant, okay? And then when the action is invariant, you consider the equations of motion, and all the consequences of the equations of motion, you have that these have to be covariant. In particular, when you compute the frequency of oscillation, okay, which is a quantity that transforms in a given way under time dilation, it goes like 1 over lambda t, because it's 1 over time. It will have to depend on your fundamental parameters, okay, for the parameters of your system, in such a way as to match the transformation property, okay? And the only way to match that is to have a relation like this times a coefficient, which of course you cannot compute, but if things are not crazy, you expect this coefficient cannot be an absolutely ridiculous number. In your Lagrangian, you don't have any such ridiculous number. So you expect this coefficient to be, let's say, order 1, okay? Even if true or not.
Riccardo, we lost you for 20 seconds. Just repeat the last few words.
I went off by 20 seconds.
Maybe 5.
Okay, so what I want to say is that, did you hear that I said that the equations of motions are covariant under this symmetry?
Yes, yes.
And all physical relations should be covariant, okay? In other words, why are covariant? Because the action is invariant. When you do the variation of the action with respect to your field or your dynamical variable, you get a quantity that transforms precisely in the complement in like that variable, right? It's like when you take a scalar and you take a derivative of the scalar, you get a vector, okay? Because the derivative transforms in a certain way under rotations, okay? So the equations of motion and the physical quantity will be covariant, meaning that the frequency must depend covariantly on these parameters. And this is nothing but dimensional analysis. Of course, I made something so simple that, you know, from the very first day you started doing physics, perhaps complicated, but I made it in such a way that it could be explained, first of all, to mathematicians. It's always good to explain things to mathematicians once in a while. Secondly, show later on that all the issues of fine-tuning we are debating, that people say, no, this is not a problem, are exactly of this nature. And the people who just say that issues of fine-tuning should not be taken into account, they should go back and think about the pendulum and pendulate as much as they can. Okay. So, and for eternity. Okay, so that's what it is. Okay, dimensional analysis is simply covariance with respect to background symmetries. Okay, and apparently this was invented by Galilei. I don't know if anybody at GGI can confirm. I am always too lazy to check that. Precisely checking the pulsations while watching. It was in the church. It was watching the lamp in the church oscillating when people opened the door, and he was checking the period of oscillation against his wrist, okay, his heartbeat, okay? And of course, he had measured G, the acceleration of gravity, and then just the question whether the frequency he was observing made sense, or at least as an order of magnitude, and of course it did. Now, this relation I'm presenting here for which is ordinary dimensional analysis, is in no way different than what you would have for the more ordinary selection rules. The one that when you say selection rules, you say, oh, atomic physics, levels, shifting of levels in an external electric field, stuff like that, transition with photons. So the typical example of a problem like this, imagine you have some atom in some spherically symmetric state, okay, some ground state, and then you slowly turn on an external electric field, okay? And now you turn on adiabatically, then your atom will end up in the ground state in the presence of the electric field, okay? And now the question is, and now the atom will adapt, it will deform, and now the atom in the new state, before it was spherical, now the atom will have an electric dipole. And now you can compute your electric dipole. And the question is, what can you say about the direction of this electric dipole? Can anyone answer this question?
Nobody's volunteering.
Nobody?
Someone wrote in the chat.
Mehmet is saying opposite to the field, okay? But why? Well, opposite is already more. Why not orthogonal? Okay. He's giving a dynamical answer, okay? Okay, that is correct, but you're using intrinsic, truly, you're really using the solution of the problem, while instead you can give the answer without, look, exactly. Giulio Gambuti is saying it's just using symmetry. Can't be orthogonal because the symmetry is cylindrical. There, correct. Well, in general, this is the result, right? You can say that the general result has this form, is proportional to the electric field times a scalar function of the electric field. And the reason for that, now as Mehmet and Tony were saying, they were saying something more. They were talking about the sign of F, okay? But that requires some dynamical information, okay? It really requires dynamical information. While even without that information, you can say right away, simply matching the transformation property of the left and right-hand side, that this expectation value has to be along E, and it should be given by a function expression like this. Why? Because it should be a quantity, because it's covariant under O3. The quantity on the right-hand side should transform precisely as the quantity on the left-hand side when you rotate your electric field. And it would be very nice if you try to give a formal proof of this, just using rotations, okay? And it is exactly the same as for the case of the pendulum, okay? So this is the typical example of selection rule. In other words, the dependence on the external parameter should match the quantum numbers of the observable you are computing. Oh, no. Oh, another example of selection rule, take the standard model. In the standard model, you have interactions that violate flavor associated to the W, okay? Here is the interaction. You have U bar, DI, W, and DJ is the CKM matrix. Now, you can think of the flavor rotations. In other words, a transformation under which each quark of different flavor is rotated by a specific phase, okay? So the phase depends on the quark flavor, whether it's up, charm, or top in the up sector, or whether down, strange, or bottom in the down sector. So you have essentially a U1. This symmetry here is what we call a U1 to the 6th symmetry, okay? It erases it. I shouldn't have erased it. Now, this is of course not a symmetry. This is a symmetry of the kinetic term, but it's not a symmetry of this interaction. Okay, it's not a symmetry of this interaction. It's only a but you can make it formally a symmetry if you assign compensating transformation properties to the CKM matrix. Okay, in such a way that when you rotate U and D, and then V rotates in this way. And now, for instance, this selection rule, okay, this symmetry imposes simple selection rules. For instance, when you consider quantum effects that generate the interaction among 4 quarks of the same type, like D, like those that enter into KK bar mixing, okay? And here you have so this is ingoing, this is outgoing, and now under this, so you know what type of operator you have here. You have like an operator with specific quark and anti-quarks of given flavors. So you know how the amplitude transforms under this symmetry, okay? And therefore you know immediately how it should depend on the V's, because the V's transform in the same way, okay? So for instance, you can immediately say this. This is just another example of so if you don't want to go and sit down and do the computation, it's just this symmetry that allows you to decide immediately, without looking even at Feynman rules, that the amplitude has to behave this way. The power and the ubiquity of selection rules induced by associated with symmetries, okay? And now this is important, and it's at the basis of all considerations about this notion of naturalness that we will discuss mostly next time, because it seems like I am, as usual, very much behind schedule, okay? And let me tell you what the story is. Let me slow down a moment, because is there any questions concerning this, by the way? not hearing anyone is absolutely. No, there are no questions. Okay. So in the examples I consider so far, okay, for each given quantity I showed you, there was only one possibility for the output as a function of our input. Okay, here as well. Okay, there was only one possibility. But in many circumstances, okay, in quantum mechanics, but even in classical physics, there can be more contributions in terms of the fundamental parameters, and I will show you an example in a moment, that match the quantum numbers of your observable. Okay, and in quantum mechanics, all that is allowed by symmetry is all that is possible is essentially compulsory. Quantum mechanics explores through the path integral all the possibility of configuration space. So all that is possible, all that is compatible with the symmetries will happen. If it doesn't happen, it's because there is some structural symmetry reason why that is not the case, normally, okay? So let me tell you what I mean here. In general, okay, let's just try to formalize this idea. Sorry, I didn't say things properly in the last 2 minutes. I somehow ran out of breath, oxygen, in this discussion without seeing you, without knowing where I'm going, okay? And this is now the conclusion of this discussion about selection rules. So consider this. In general, a given quantum system will be endowed with several couplings, okay? Which could be like the electric field in the example of the hydrogen atom. It could be the couplings in the standard model. It could be more things, okay? These are your couplings, okay? And then you do a path integral, you do a computation in quantum mechanical computation, you compute an observable, okay? An observable will be affected by, if you want to think in terms of Feynman diagrams, many amplitudes. There will be many contributions, and in quantum mechanics, all things interfere, all these contributions add up with certain coefficients, okay? So now, this method contribution will be just what? Functions of your, or expression that normally in the simplest case are just polynomial expressions or monomials of your couplings, okay? And basically each of these contributions will be some product of this coupling. This is in the simplest situation with a coefficient, which is just a numerical coefficient. A numerical coefficient can be 100, can be 10, can be 10 to the minus 2, but there we can call them order 1. They're just numerical, okay? And then there are the couplings, okay? The couplings could be large, could be very small, okay? And it happens precisely what I showed you in the last 3 transparencies, that this relation between the observable and the input parameters, the coupling, will be covariant under whatever symmetry you can think of, okay? So you will have an expression, okay? Your expectation value of your observable will be a combination of expressions that transform in the same way as your observable under all the symmetry you can think of. So you will have all these contributions, and now there are 2 situations that you can think of truly quantitatively. Forget this sentence here. There are 2 things that can happen. Either the quantity that you compute when you measure it, okay, when you measure this quantity may be much smaller than the biggest of these contributions. Okay, it could be much more than the biggest, or it could be of the order of the biggest. If it is the order of the biggest, that's it. Okay, that's normally what you said. There are many contributions, one dominates the other. That's it. It seems like Okay, this I will ask later. We will answer later. Okay, so so you can have that's a normal situation. On the other hand, there could be a situation where you have a few, at least two big contributions comparable in size that cancels almost exactly in such a way that the thing you measure is way smaller than the individual contributions. Okay, so let's consider this second situation. Okay, what can happen in this situation? I mean, what can be? Well, there are two possibilities. Perhaps we overlooked the symmetry. Okay, there is some symmetry that we have that still relates this contribution in the sense that according to the symmetries, these two contributions that cancel one another should be packaged together and be considered just one. Okay, in that sense, it's just one contribution that is small. Okay, or maybe not, or maybe there's really no symmetry that we can think of our system, even including all the symmetry transformation of the parameters, where we can really relate these two contributions by symmetry. In this situation, we say that there is some fine-tuning, okay? And it is the practice and the nomenclature of particle physicists to call the first situation, the situation where it is the symmetry that is telling you what's going on, we call it natural, okay? And the second situation, which is possible, okay, which is, it doesn't mean that it is impossible, which is still possible, but it's atypical, we call unnatural. Okay, so these are the two main ideas. Okay, in other words, at the end the sentence that I wrote here, it basically making sense. Okay, if you want, it seems that if you compute all these contributions and you compute them, and then or sort of you seem to be knowing them, but then you know that the measured result is much smaller, it looks like you're missing something in the picture. Okay. Maybe you're missing a symmetry, or maybe you're missing this cancellation. And each of these things may mean something, okay, in a way that I will now try to illustrate, okay? Somebody is asking here, no, 10 to the 20, no. Somebody is asking, why can't the coefficient be 10 to the 20? Yeah, you could have some very tiny coefficients in some effects that are non-perturbative, but so you can have effects that go like e to the minus a coupling. Those certainly can go, but often you can associate this very quantity here itself with some scaling properties. It means that if you call this your lambda, then you have a more direct view of what's going on. So. But large coefficients, no. Small coefficients, maybe, but we don't have examples. Okay, we don't have examples of that. Why can't you get some coefficients that are very tiny? That's in a sense a good question. Let me give you an example. Okay, let me give you an example. Let me give you first an example of a natural situation. This is given by the pion mass, and okay, what is the situation here? Again, you have this fundamental theory. The fundamental theory is QCD, which is made of quarks, gluons, and the photon. What the hell is going on here? Okay, the quarks, gluon, and the photon. Okay, and talk like this. Sorry, it's very hot here. Let me get my shirts off. It's very hot in here. Okay. Okay. So you have the microscopic theory is the theory of quarks, gluons, and the photon. Okay, and this theory has one coupling, which is the strong coupling, which becomes strong around 1 GeV. There you have a rearrangement of degrees of freedom, as I said. And from that scale below, you have bound state, the mesons, the pions, and the photon. Now, at the scale where relevant for these dynamics, of course, the whole theory has infinitely many parameters, but at this scale, only a few matter because the vast majority of them are associated with high dimensional operators and they are invisible. And the only parameters that matter are 4 of them. It's lambda QCD, which is the scale of the strong interactions, and the masses of the quarks, and the electromagnetic coupling. So these are your parameters. And there are 2 basic symmetries, if you want, the one I forgot to write. One is the chiral symmetry, which is the symmetry under which the quark field transform. And the other is dilatations, if you want. You can think of. Of course, both these symmetries are broken, okay? Both these symmetries are broken. The chiral symmetry is broken by the quark masses, okay, because they transform under this symmetry. And dilatations are broken because there are dimensionful objects, right? The QCD scale has dimension of energy, so it scales with dilatation with charge 1. It's an object of charge, of dilatation charge equal to 1, similarly to the quark masses. Okay, so dilatations are broken in an obvious way, and that's just, and fixing the quantum numbers of dilatation is like just doing dimensional analysis. But also you can fix the quantum numbers of the chiral symmetry. Now, how you construct your effective Lagrangian? Okay, your Lagrangian is precisely constructed. You can view your effective Lagrangian here as an observable that you compute as a function of your input parameters. So it will precisely respect the selection rules I mentioned before. The construction of the effective Lagrangian will be done respecting the selection rules. So the Lagrangian will be formally invariant under this symmetry, provided you let also the parameter transform. Okay, and this is precisely the rule with which we build the chiral Lagrangian for pions, and it is the basic of basically all the predictions we are able to make about pions. Okay, selection rules. Now, how does this work? Well, you know, the pions are the Goldstone boson of the symmetry breaking. SU2 course SU2 broken to U1, this to SU2. This is the isospin SU2, and the pion field is just given by a 2x2 matrix in the following way, which transforms like this. Okay. Now, just looking at the quark Lagrangian, you can assign compensating quantum numbers to the quark mass as if it was itself a field. If you assign to the quark mass, which is this 2x2, I'm just looking at 2-flavor QCD, this transformation property, then the QCD Lagrangian will be invariant under chiral transformation. Similarly, there is electric charge. Electric charge breaks also the chiral symmetry, and the existence of the electromagnetic interaction is simply quantified by the fact that the derivative of the pion field is actually a covariant derivative, where the photon field enter with these charge matrices, which are just the charge matrix of the quarks. Okay, this is the charge matrix of the quarks. And now, if you treat as they are, these Qs are fixed parameters, this breaks the chiral symmetry. On the other hand, if you formally allow these charge matrices to also transform under the chiral symmetry, then this derivative transforms covariantly under chiral transformation, and using it, you can construct invariant Lagrangian. Now, putting together these elements about chiral symmetry, together with dilatations, which
Riccardo,
is just about matching dimensionality of coefficients in the Lagrangian, you can construct your effective Lagrangian. And
Riccardo, there are 2 questions, maybe before that you discuss that.
This one on the QCD. Normally here there is, if perhaps the person who asked about the 10 to the 20, I will tell in a moment why here I'm doing this, where this is expected to be of order 1.
Ricardo, can you hear me?
Yes.
There are 2 questions maybe before that you.
Yeah, I know, but if I start answering all the questions, I cannot finish.
Okay, we
can do it later?
Discuss it to the end. Yeah.
Yeah,
okay.
Can I do it later?
Sounds good.
Yeah, I tried to answer the question before, and I realized that this brought me off, and now it took me some while to get back.
Yeah,
Because
let's
these questions are very articulated, some of them, and it requires time to answer. Okay, so you match all your coefficients, okay, and it's just a question of practice if you want, but I can explain the tricks by which you can determine them. All these coefficients are instead of order 1, okay. If you want, the reason why this coefficient here is 16 pi squared, it's very simple. You want to have, you know that these pions exit from strong interaction at this scale here. So you want to match the coefficient in such a way it reproduces some interaction that becomes strong around 1 GeV. If you put here 16 pi squared, you precisely have that. You have an interaction among pions that becomes strong precisely around lambda QCD and becomes weaker below. Okay? If you want this match roughly the strength. And this coefficient here is of order 1. Why? Well, it's of order 1 because the perturbation due to the quark mass must become of order 1 when the quark mass is of the order of lambda QCD. In that case, when you are at energy of order lambda QCD, these derivatives and this coefficient here play the same role. This is why. And here as well. Here you put this because this effect, given that you don't have photons in the game, you only take into account virtual effects of photon, you have exchanged a photon loop. And when you integrate over the virtuality of photons that you exchange, in 4 dimensions, you get 1 over 16 pi squared. Or in other words, you know that if the photon coupling had been strong, that is to say equal 4 pi, this would be an order 1 effect. So if you put here 16 pi e squared over 16 pi squared, you know that when E becomes of order 4 pi, this effect is strong, as it should, right? It becomes of order lambda QCD. So the fact that all these coefficients can be argued to be of order 1 can be done, okay? It requires a little bit of it's like an art, okay? But you can do it, okay? And it works very well. And now in this, this system is simply the analog of the pendulum. It's just the quantum field theory pendulum, nothing else. And there are several symmetries that enter here. There is the chiral symmetry and dilatations. In the pendulum, you have time dilation and space dilation, but conceptually it's exactly the same thing. And now when you compute, the implications are the same as those first appreciated by Galilei that time when he was in church. I don't know whether during the service or not, but he was clearly bored by what was going on, and he was inventing dimensional analysis. Okay, so you have a leading contribution, which is the well-known Gell-Mann-Oakes-Renner relation for quark masses, for pion masses, and then you get at the next order in the quark masses. It turns out that the quark masses are small parameters. Okay, it's just a fact of life. Quark masses happen to be small, much smaller than lambda QCD. Numerically, and E also happens to be weak. We may debate why it's that, but it's that, okay? So E is small. So at the leading order, the pion, the charge and neutral pion are degenerate, and their degeneracy is broken only the next to leading order when you take into account either quadratic effects in the quark masses or the electromagnetic coupling, which is weak. Okay, and this interaction here, okay, so here you have precisely an example of 2 terms, okay, that contribute to the same quantity. It's precisely like in what I discussed before, where you have 2, okay, you have a sum of contributions that come from very different, apparently different sources, okay, and as far as we know, okay, in fact, we know very, very well, this term is much bigger than this one. And it dominates. Okay, so you have 2 contributions. There's no cancellation. You have what we would consider a typical situation. In fact, situations like this one are ubiquitous. Compensate for that, and you have a cancellation. But actually, as far as I can tell, I don't know whether we know whether this, in order for that to happen, this C3 should be negative. And our knowledge of this term, I believe, is not allowing us to say whether it's positive or negative. But if it were negative, then we could imagine a situation where this contribution cancels that, And where we have two apparently unrelated contributions that are satisfy the same covariance, that transform in the same way under the symmetries of the system, they are unrelated because one is the quark. I mean, at the level of the standard model, maybe in string theory they are related, but in the standard model they are unrelated, and they compensate one another. This doesn't happen. Okay. In fact, something, however, not far from this, but it really doesn't happen. A situation where this contribution as the opposite sign arises in the proton-neutron mass difference. There you have, again, two contributions, one electromagnetic and the other the quark mass difference. And there they happen to be comparable in size, but they don't cancel. Okay, it's already amazing that they are comparable. Okay, in fact, the fact that the quark wins over the electromagnetic is what ensures that the neutron is heavier than the proton, and therefore the neutron decays in the proton, not vice versa. Otherwise, there would be no hydrogen. But again, there's no example of a fine cancellation. I should say that this contribution here, which I estimated using dimensional analysis and selection rules in a careful way, I could have guessed its presence without making any mistake, simply by doing some naive computation in the effective theory. What I could have done, I could have taken the effective theory for the pions, okay? And now you see the pions now have a photonic interaction. They interact with the photon. In fact, only the pi plus interacts. The pi zero does not interact because it's neutral. And now in this effective theory, you may perhaps naively try to compute the quantum correction to the pion mass due to its electromagnetic self-interaction, okay? So you compute what is known as the self-energy. At leading order is just a one-loop diagram, which comes from exchanging a photon. Okay, you sum these two diagrams, and this should give you at zero momentum the correction to the pi plus mass. You do this computation, and you find you can easily see you have like this one here. You have these two diagrams contribute in a similar way. Okay, this you have one propagator 1 over p squared. Okay, and you have integration over the momenta is d for p. So what you have a diagram that formally is dominated by large momenta. It means that the contribution to this mass cannot be computed in this effective theory, because this contribution is dominated by a range of momenta, which is the highest, which is basically dominated by the range of momenta where the effective description in terms of pion breaks down, and the pion theory merges into the more fundamental quark-gluon theory. Okay, but you know that this scale exists. Okay, and what would you expect? Well, the pion is a composite object at distances much shorter than the inverse QCD scale, which is to say at momenta much bigger than the QCD scale. This computation doesn't make sense. So what is the best guess of how to make sense of this integral? Well, the most obvious thing is that this integral gets cut off at the maximal energy at which we can talk about the pion. Okay. Of course, this result is a very rough estimate. You do it and you get precisely this. Is this magic? No, this is not magic. This is just dimensional analysis and selection rules. Just by doing this dumb thing here, you are implementing the selection rules I was telling you before. Okay, and but it can be done more quickly without doing all this song and dance, all this crap here. It took me three hours. I just sit down, I compute this, and I get that. It's the same result. And normally this is presented as, oh, there are quadratic divergence, blah, blah, blah. No, that's one way to say it, but this is misleading. What you're doing is just estimating a contribution using symmetries, nothing else. This is the typical situation in particle physics. Other examples of this are the KK bar mass difference. I could go on with many examples. From different sources if you want, and that can cancel one another, okay? And they can cancel one another with arbitrary precision. This, in our experience, happens, or to good precision, happens all the time whenever we have many choices, it's the usual story, right? If you have many systems of this type, okay, if you have many systems of this type, if you have many replica of similar systems, there ought to be one system where accidentally you have this cancellation. Okay, this is just the step. A generic one taken by chance, I mean, how can you have a cancellation? It's unlikely. But if you have many, then you can go in this many and pick the one where has the cancellation. And this is what happens often. In fact, it's the interesting thing that people study in many condensed matter systems. Okay, let me give you an example. Okay, so what I'm saying here is that in the normal lab practice, this extreme fine-tuning is associated to the existence of a large set of options for which we can pick. And this large set of options, we can call it a landscape of possibility. Let me give you an example, okay? Consider one of the a typical quantum ferromagnet, okay, which has some quantum critical point. This is the system. I found this in a talk given by Sachdel at the Higgs Fest symposium a few years ago, okay, but it's a paper of 09. So what you have, this system is an antiferromagnet, okay, which means that you can describe it macroscopically in terms of a field, which is simply the spin taken at each point, but depending on when you switch from one point to the next, you reverse it, okay? So normally they tend to go in the opposite direction, but if you consider a variable which is multiplied by this, where x and y are the end positions of this two-dimensional layer, okay? So essentially, it's like a ferromagnet, okay? If you just look at phi, it's very similar to a ferromagnet, and this system will have a potential, okay? First of all, I should say that this system is a crystal. So like all crystal, you can put it in a, I don't know how to call it in English. Riccardo, com'è una morsa? Come si dice morsa in inglese?
I have no clue.
Like one of these things that puts pressure, the thing that where you crank and so you crank the pressure, okay? If you crank and you change the pressure, this system behaves after a critical pressure in different ways. So at very high pressure, sufficiently high pressure, it behaves like what is called as nil antiferromagnet, which is essentially like a ferromagnet. In other words, rotations are broken and the spin is polarized in some direction, like in an ordinary ferromagnet. It's ordered in one direction. And below a certain pressure, it behaves like a paramagnetic. In other words, there's no local magnetization. Okay. In fact, the near side, they tie together in dimers that are singlets of rotation. So the system is macroscopically rotational invariant. And the way it works is that this system is like an ordinary scalar. It has an effective potential where the couplings, in particular the quadratic term, they depend on the pressure, okay? They depend on the pressure. And in particular, there is the mass can cross at a given specific value of the pressure can cross zero and change sign. When this happens, you go from this phase to that phase, okay? You have symmetry breaking. So what happens here is that this M0, the typical value when you don't choose the specific pressure, is the typical value of the mass of this degree of freedom that you can deduce by simple dimensional analysis based on the atomic physics that makes up this molecule. Okay, of course I would not be able to do it in detail, okay, because this is a slightly complicated thing, but roughly you can estimate it. Okay, so this is the typical can exist in a landscape of pressures. Okay, so there is a continuum of value of the pressure for which a crystal can exist. That's a very peculiar thing. It's like the system as a continuum of stable states that depend just on the boundary conditions. And this is a specific property of solids, okay? And it has somewhat to do with the fact that solids are objects that break translations and their description in terms of macroscopic degrees of freedom. But they have this property. They have this specific property that they exist in a landscape on a variety of values of the pressure. They don't have a single ground state, okay? The state where they are depends on the external pressure you put. And using this landscape, you can choose a specific point in the landscape where you have two different contributions that normally they don't cancel because they have different, they don't have fully the same origin, but they're part of the same. They are. When P is very, very small, they can be viewed as different contributions. At the end, they're all part of the same physics. But by choosing, so the normal expectation for this mass would be this based on simply selection rules. But by choosing a specific point in this landscape of pressure, you can choose one where this is zero. At that point, you have a value for this mass, which is really undoing all expectation of selection rules. Everywhere else, you have that. Okay, but in order for this to happen, in all the cases we know, we have this sort of multiple possibilities. Okay, so tuning, so the existence of this cancellation between things, between contributions that have the same properties under symmetry transformation seems to occur in our experience always when, and understandably, when we have multiple possibilities, like this example I'm presenting here. So we can say, as I say here, that we can undo the natural expectation from atomic physics by tuning the pressure at a critical value, okay, P equal PC, in a landscape of possibilities. That's an example of a situation where you undo the natural expectation, okay, and this we call a fine-tuned situation. But again, this is in this example, this fine-tuned situation is precisely associated with some structure, the existence of multiple choices. Okay. I think I can stop here.
Yes,
I think I really went over time. Right.
Yeah, so maybe there were these couple of questions, and then I don't know if there are other questions, but there was one question.
Well, the first question was about the dimensionality of coefficients, the size of coefficients. Somebody asked, why can it be 10 to the 20? So I cannot give you I don't think I can give you an answer to this question in general. I can give you an answer to this question on a case-by-case basis. And in the case of the Lagrangian I showed you before, I gave you the quantitative or semi-quantitative explanation for that. Okay, and you may call this physics common sense, fine, and you may not be happy, but I cannot offer more than that, but it works. Okay. In general, I would not be able to answer. I mean, you really need the context to give a general answer. So now the other question was the naturalness you are referring to. This is the same as technical. Yeah, I'm trying to give. Maybe I'm failing. I'm trying to give a more modern assessment of tough naturalness. After all, tough naturalness was introduced 40 years ago. I'm trying to, at the end, the idea is the same, okay? And I will discuss more next week, and then next lecture, okay? But in the end, yes.
Yeah, then there is another question in the chat about naturalness. By Daniele.
Yeah, he's asking, well, so everybody sees the question, right?
Yeah.
So you're right. If we don't know, okay. If you may say that if there is no landscape, okay, if there is only one possibility, then it seems like in all the examples we see, like the pion mass, we would notice, we will be very, look, in the example I presented, when there is no landscape, there's no cancellation. When there is cancellation, there is a landscape. In this example, the pion of or condensed matter systems. Now, we will see later when we go and talk about the Higgs, we don't know, but in the example we see, it seems like the absence of a landscape would suggest that cancellation seems very unlikely. Okay, the presence of a landscape makes cancellation possible, perhaps not likely, but possible, and maybe there is an explanation for that, which we may have to do, we will see later. Well, I don't know whether we will discuss it, to either cosmological evolution or the anthropic selection rules. But I don't want to get into that at all. I'm just presenting you some facts, and we may or may not want to draw the moral, but the facts I'm presenting is that in what we see, selection rules are undone whenever, at some effort, also some effort, but whenever there is the possibility of a landscape.
Yeah, my question is, but without this distribution of probabilities for...
No, I never talked about probability. I never discussed probability distributions.
But likely...
I didn't want to get into this.
No, okay, but likely, the word likely, this cancellation is...
Yeah, okay, yes, you're right, plausible. Okay, let me just say, instead likely, say plausible.
Okay, because this seems...
Let me use another word, plausible.
Okay, I see.
Yeah, let me use the word sorry, you're right. I should not use likely, plausible.
Okay. Because the fact was that in my view is more, if I have more parameters between one I could choose, okay, I could choose the right one, but it would be likely that in this random universe, I don't choose the right one. But if I do not have any distribution of probabilities for parameters, this could be just the right parameters and to cancel out the contribution. Okay, maybe it's less plausible, but not less likely, because for saying likely, I need to say this value is more.
Let me just say plausible. Sorry, I used the wrong word, plausible. It would be surprising that, look, let me put it this way. Imagine we had found imagine we had found in the pion Lagrangian that C3 and C4 cancel exactly. They cancel at 10 to the minus 20. What would we do?
Yeah, I understand that
So this is a hint, right? It's a hint that there is something that we're not understanding, perhaps.
Yeah.
Maybe it's just an absolutely crazy thing that happens with no reason. But perhaps there is some truly underlying relation between M up and M down and E and lambda QCD that can only be seen in a more fundamental theory, which we do not possess. Or maybe there are many choices of these M up and down and E and lambda QCD, and we ended up in the choice that gives you 10 to the minus 20 cancellation because of the way we got here. Because of the history of the universe, we ended up here in some cosmological evolution, and in some way, cosmological evolution selected this point. Okay, now for the pion, it's hard to imagine anything like that, but this could be a possibility. Or we could decide that this is not an issue we care about and go and study flowers. Daniele, you see what I'm saying?
No, sure. I see.
Now, in the case of the pion, if while doing physics, and studying its interaction and try to understand the parameters of the pion effective Lagrangian, we could have done this, okay, and would have said, oh, look, we can explain the mass of the pion if there is this scale lambda QCD at 1 GeV, well, then there must be something at that scale, and we would have been right. You see?
Yes, yes, I see, of course, of course.
We would have been right. That would have been a good way of arguing, right? I'm not telling you that this should always work, but at least in the cases I can give you example of, it seems like when it doesn't work, it's because there is, like in this condensed matter system, that there is some very clever lab technician that came and chose the pressure and put it here.
Okay.
By choosing in a landscape of pressures.
Okay, I see. No, sure.
Now, I'm developing ideas based on things that we see. It could be, when we get to the hierarchy, that is not tractable with the things we can understand at the moment. You see what I mean?
Yeah, sure.
Maybe all I'm telling you for the Higgs mass is complete crap, both the landscape, everything. But at least we need to know what we can say before saying something new, right?
Okay.
So
yeah.
So yeah, that's essentially what I'm trying to do.
No, sure. Yeah, I was, okay. Yeah, of course, this cancellation is not impossible, but one would, if this cancellation occur, one would try to look further into this cancellation.
Exactly.
Then, if there is more physics behind.
Yeah.
Okay, so there is also another question by Noam.
Thank you very much.
Yeah. Where is it?
Hi. No, I can talk.
Okay.
Can you hear me?
Yes.
Yeah. I was just wondering two things. One is when you talked about the chiral Lagrangian, you mentioned also that dilatations are broken, and you didn't talk about the Goldstone boson of dilatation. So I was just wondering what is.
No, there's no Goldstone boson of dilatation because dilatations are broken by parameters that are not small. So you see, dilatations are broken by. If you wanted to worry about the Goldstone boson of dilatation, yeah, you can. You would be worrying about the parameter. So first of all, the issue of the Goldstone boson of dilatation is a delicate one. Okay, because the Goldstone boson of dilatation is the only Goldstone boson that has a mass among all the Goldstone bosons. So saying the dilatation is spontaneously broken. And so the issue of spontaneous breaking of dilatations is a very delicate issue.
Okay.
First thing. Second thing, dilatations are not even an approximate symmetry here. So if even there were a Goldstone boson, given that the breaking is order 1 on the scale of QCD, then the mass would be order lambda QCD, which is to say heavier than the mass of the pion, therefore outside of our effective theory.
So in terms of this theory, it would be an explicit breaking of the. It would be.
It's a situation where the explicit breaking is so large that yeah, there's no issue even of talking about the. It's very much as if let's say that if the quark mass were 1 GeV, then you would say that there is not even the point of talking about this other symmetry.
And the second thing I wanted to ask was just about earlier when you were sort of showing the diagram of having a scale invariant theory between confinement and the UV, and going from scale invariant theories while having a mass gap. Is that what people talk about when they talk about the conformal windows? Or is that something
right? The conformal window is a specific point. The conformal window is conformal window saying QCD. You're saying, Noam.
Yeah, I got muted. Sorry.
The conformal window in QCD, you mean?
Yeah, because that's. I mean, it seems to me that many theories could lie in this scale invariant region. And
yeah. The conformal window of QCD is a particular value of n flavor, okay, which is between the or minus 2/3. and flavor, right? And close to the point where so there is a okay for n flavor less than, I believe this is 11 halves in color, and bigger than some number times n color, but less than that. What happens is that the QCD or a theory like QCD has the following RG flow. So so let me say the following. I'm trying to decide how to draw this. I'm sorry, no, I'm trying to think what to say. So I should say the first thing, when a theory, let me say the following now. Let's say, when I'm saying conformal field theory, okay, plus, let's say G relevant, alpha or alpha, plus G irrelevant, alpha or alpha or A irrelevant, okay? So I can always write my theory in terms of the fixed point CFT, Lagrangian action and deformations, okay? Now imagine I choose all these G's to be exactly equal to 0. Are you with me?
Yeah, I hear you. Yeah.
So if you choose this to be all exactly equal to 0, then when you go at high energy, you will only have the relevant ones, and these they decrease because their effect grows when the energy becomes small. So if you set to 0 all the irrelevant couplings, okay, then your theory can really be extrapolated to arbitrary short distances. Okay, so in a sense, it can be a complete theory. In fact, our modern understanding of UV complete theory, the one that we would call truly renormalizable theories, which make sense of quantum field theory with an infinite cutoff, are conformal field theories where we have set to 0 all the irrelevant couplings. And then what happens in these theories is that, okay, if you look at the flow I was showing before here, let me copy it here. Okay, so what we do, it means that we start the RG flow in the far UV at 0 value of all the relevant couplings. And then we start evolving toward the infrared. And some coupling grow, in particular, the gauge coupling can grow, okay? Now, what can happen when this coupling grow is one of two things. It can the theory can either confine, form bound states like QCD, or it could reach a new fixed point in the sense that it could be that here there is another fixed point you flow into. So in other words, instead of doing, so you have a flow like this, here the UV fixed point, and this is the IR, and basically you flow. And when you reach here, you reach this new fixed point, and this is what you call the conformal window. And at this point, the theory is described by another. So, well, here is described by the free quarks and gluons, and here is described by strongly interacting scale invariant theory of quarks and gluons. And then, of course, as seen from this fixed point, it looks like the couplings here are irrelevant. In other words, when you go towards here, all the deformation that you are here goes to 0. In other words, it pushes you inside the fixed point. You flow inside. And this is a fixed point at finite value of the coupling, okay? And yeah, but this could be one of these things. I don't know whether I explained it clearly.
No, thanks. I mean, it explained this, at least this specific example. I could ask about if there are other examples that we know, but I think it's we're over.
Well, for instance, in the case where NF is close to this endpoint, you can really, and is large, you can really do all these in perturbation theory. These are the well-known Ben-Sachs fixed points.
Okay. Thank you.
Yeah, maybe we can also continue the discussion during the discussion session. Riccardo took notes in Slack.
Then we
so-
can treat in perturbation theory.
Okay, yeah, so I was saying that we can continue this discussion also during discussion sessions. And yeah, Riccardo took notes in Slack, and there we can add additional questions as well. So yeah, I think we can finish here for today. And thanks, Riccardo.
Yeah, there's no discussion.